All right, so what we're doing today is we're going to take one step further in applying what we had done yesterday with the solids of revolution. And basically, the difference between what we did yesterday and what we're doing today is yesterday we were creating a solid that was solid all the way through. Here we're actually kind of creating containers. Or sometimes they're open on both ends, but we're creating things that are not necessarily the same shape on the outside as they are on the inside. Okay? So here, for example, you see we have the graph of y equals the square root of x. And then we have this y equals x squared. And it creates this kind of leaf shape. And then we're going to revolve that around the x-axis, okay? So you can see, like down here at the origin, when we revolve this, it'll actually be kind of infinitely thin, okay? Because it's just meeting at a point there. And out here on the edge of this circle, it's going to be like razor thin, okay? It's going to be really, really thin. But you'll notice in the middle, we've got like this bulge in the middle that's a result of having, this leaf shape, okay? Now, what ends up happening here is that, this is how we can make certain containers or whatnot. We can make it look one way on the outside, another way on the inside. Maybe we wanted it to look like just a plain cylinder on the outside. Someone looks like it looks like a cylinder, but on the inside, maybe we want it to have like a funnel shape or something like that. We could do that by using two functions like this, okay? Now, I want to develop this idea, because if you understand where this comes from, it'll be really easy to remember how to do it, okay? If you recall, our formula for the area between two curves was the integral from one intersection point to the other of the top function minus the bottom function. Okay? So, for example, on this one here, the top function, and again, when we're talking about top or bottom, we're just talking about within the interval that we're dealing with. This square root of x would be the one on top. So if I took the integral of just the square root of x, that would give me the area all the way down to the x-axis. Okay? So, again, the integral of the square root of x from 0 to 1 in this case would give me the area. If I wanted to find the volume of that area revolved around the x-axis, I would make it a pi times the square root of x squared. Okay?
What does that give you again?
That would give me something with the same outer shape as what we're going for, but it would be solid on the inside.
Okay, are we looking for the volume right now?
We are going to look for a volume, yes.
Okay.
Okay? We want the volume of this 3D shape over here that has this kind of, bulge, and really we'd be looking at the volume not inside, but the volume of material it would take to make it. Okay, so maybe we're going to make this thing out of plastic so that we can now know exactly how much plastic it's going to take to build this thing. But that's going to be too much. That's going to make it solid in the center. So what we need to do is we need to cut out the area below. Okay, if we look at this here, here's the x squared, all right? In order to just rotate the area we want around it, we're going to need to cut off all of this, okay? And as a result, if we cut off the volume of that rotated around the x-axis, then our final volume will just be what we're looking for. Okay? So notice, to get that volume, it would be the integral from 0 to 1 of pi times x squared dx. Okay? And that's right. How would we get rid of it? We're simply going to subtract. Okay? So you can think of it almost like the top function is like an outer shell, and the bottom function is the amount that we're cutting out of it. All right? So we do this subtraction, and that'll give us the volume of material it'll take to build this thing. How would I figure out how much this thing will actually hold?
Oh, you find the total area and you subtract it. Not area, the total volume. And you subtract it by that.
Okay. Yeah, and that's right, actually. If we got the whole volume and subtracted this thing here from it, it will give us the volume inside, but it'll actually end up equaling just this, okay? So this right here is actually how much our container will hold. This volume right here. So we have this volume total, we cut out this much so it'll hold that much, but that's how much we're getting rid of, and the volume of the material that it's taking to create this big bowl is going to be given by that whole thing, okay?
So now we're just integrating it.
So now we just integrate it. Now, I don't even really want to finish this one completely, but I want to use this to develop a formula that's a little bit easier to use, okay? So watch this. So let's look at some of the properties we have for integrals. First of all, I have a constant pi in both of those. And you guys know that you can take a constant out of the integral. So we can rewrite this as pi times the integral from 0 to 1 of, and I'll simplify this a little bit, that's going to be x, minus the integral from 0 to 1 of x to the 4th. Okay? So I pulled the pi out. Okay? Now, another property of integrals is that if you're adding or subtracting integrals, as long as the upper and lower boundaries are the same, you can put them together or take them apart. You can put them together into one integral, or you could take them apart into multiple integrals. Here, I'm going to actually put these together into one integral, x minus x to the 4th. Okay? And you notice what ends up happening here. Check this out. What ends up happening is we get this formula. The volume of the area between two curves revolved around the x-axis will equal pi times the integral, and we'll just say from a to b, of f of x squared minus g of x squared dx, where f of x is greater than or equal to g of x on the interval from a to b. Okay, if they overlap and switch, we'd need to break it up. Okay? But the top function, the greater function comes first. So we do f of x squared and we do g of x squared and we subtract them. Okay?
How can we find out which function is greater if we don't have a graph?
If you don't have a graph, you could simply plug in any number in between a and b.
Okay.
Like here it's 0 to 1. If you plugged in a half.
And which number is greater, that's going to be the greater. Okay.
Yeah, like here, if I plugged in a half squared is a fourth. The square root of a half is root 2 over 2, which is like 0.7 over 707. Yeah. Okay, so obviously the square root function is the greater function within the interval. Okay, so yeah, if you can't see it or you don't have the graph in front of you, then you just plug something in.
Plug in the same number, right?
Yeah, plug in the same number for them. Okay? Does that make sense so far? Okay? So let's work out an example all the way through here. Here's a little more formal version of the formula. You'll notice here they call it y sub u and y sub l, so upper and lower function. Or they say here that f of x is just greater than g of x. All right. So here we have a shaded region between y equals 4 minus x squared, that parabola you see, and the line y equals 3, the horizontal line. So we're taking this area right here, and we're going to revolve that around the x-axis. So it's going to, in the end, we're going to have something, that kind of looks like, I don't know, maybe a wedding band or something like that. And it'll kind of be rounded on the end. See that? That's kind of what we'll end up with here after we're done revolving this. Okay? So, the first thing that we need to do is we need to figure out what the interval will be that we're going to integrate over. Okay? To find the interval, we need to find these x values here. It says find the coordinates of a and b. The nice thing is, since it's the line y equals 3, I know it's going to be something 3. Okay? So remember, how do we find the interval when we're doing area between two curves?
Don't we plug in the numbers?
How do we find the interval? A is the point where what happens?
Where it starts.
It starts, okay. Why does it start there?
Oh, because they intersect.
Because they intersect there, okay? Sometimes we'll be given like a vertical line and you'll go up to that line. Other times, like this one, they'll just say it's the area between them, and that's where you got to use the intersection points, okay? So, to find the intersection, we're going to find 4 minus x squared equal to 3. So we get x squared equals 1, and x is going to be plus or minus 1. So, as a result, A is negative 1, 3, B is 1, 3. When we find for part B the volume of revolution, we're going to take the volume equal to pi times the integral from negative 1 to 1 of the f of x squared minus g of x squared.
Is there any way you can take the volume of revolutions of y instead of x? Not in this case, since they're both.
There is. We're using.
We're not doing that though, right?
Yeah, we're using. There's the disk method and the washer method.
Uh-huh.
The disk will write it in terms of y, and then it'll integrate along the y-axis. That's one method. We don't do that for IB.
Okay. So if we're given
but-
y coordinates, we plug it into the function to find the x.
Yeah, that would be best,
Okay.
unless you're really confident that you remember
No,
how
I
to
don't.
do that. But yeah, you can. It's just not something we cover in this So yeah, we have this integral from -1 to 1. So what are we going to take the integral of?
F of x squared minus g of x squared.
Okay, f of x squared minus g of x squared. F of x is the upper function, right? So which one is that?
Y equals 3. No, never mind. It goes above it.
Yeah. Notice here the parabola goes above our function, okay? The parabola goes above our line, y equals 3. Okay, so we're going to take the integral of the 4 minus x squared minus 3 squared. Okay? 4 minus x squared minus 3 squared. Okay? Now, why don't you guys try to take it from there and see how you can do with that?
He looks at a
All right.
rainbow, all he sees is a black stripe.
So, let's take a look here at what you guys did. What'd you do first when you went to integrate this?
I foiled.
Yeah, we'd need to FOIL. It's not a linear function inside the square, and this isn't set up for u substitution, so we'd have to FOIL that out. We still got the pi here. We're going to take the integral from -1 to 1 of, you have a 16 minus the 9, so that would be 7. I'll simplify a little bit here. Minus 8x squared plus x to the 4th dx. Okay, so we're integrating from -1 to 1 of that. So that's pi times 7x minus 8x cubed over 3 plus x to the 5th over 5, evaluated from -1 to 1. Okay? So, pi is still hanging out here, and we've got evaluated at 1, it's just 7 minus 2 2/3 plus 1/5. Okay, minus, if I plug in a -1, it's minus 7. -1 cubed is still -1, so minus a -8/3 would be a plus 2 2/3. And then -1 to the 5th is a -1, so it's minus 1/5. Okay? So now we have pi times, it's going to be 7 plus 7 is 14. 14. Negative 2 2/3 minus 2 2/3, that's a -4 4/3, or -5 1/3. And then 1/5 minus a -1/5 is a plus 2/5. Alright, so now we just have to simplify that portion. That's going to be 8 2/3 plus 2/5, which is 8 10/15 plus 6/15. So that's going to be 9 1/15. Okay, 9 1/15 pi. And that's going to be cubic units, whatever the units are. Okay?
Can we leave it as an improper fraction?
You could, if you wanted to make that, would that be 136 pi over 15, that's fine.
And if they don't give us the unit, do we just use u?
Yeah, you could just use u.
Okay.
Honestly, on the exam, they don't care if you don't put any units, unless they're specifically asking for that, but
Okay. So I foiled in the first step, but can you just repeat why you can't do u substitution?
the u in this case would be a 4 minus x squared, okay? 4 minus x squared, I I should say, we can't use substitution with our methods. I know du would be negative 2x dx. Since there's no x in here, I know there's a way that you learn in like AP Calc or whatever that you can do stuff where it's not there and whatnot. It's a little more advanced, but for our purposes, we wouldn't be able to do that. Okay. All right, any questions, comments? Jessica, any questions? Well, that's right, you're not here.
Gross.
All right,
Oh, you're
you can
talking to
ask
me, I was
later.
like, oh, okay.